everybody got a midterm grade because that's now the policy, apparently. Even though the last email I got said everybody below a C- should get a grade. Now it's everybody gets midterm grades, just so that you know. And then if not, the registrar yells at us, which I've still got one class I've got to make up grades for. But you got where you stand now in lecture and lab. Okay, so where were we at last time? Which is a good question. We were talking about electrophilic aromatic substitution and how we're going to add an electrophile to the ring. So just to go back, where's the screen? There's only one person that's more stressed than I am right now, and that's Dr. Wainer. So if you see Dr. Wainer, go the other way. Because we're having a meeting here this afternoon, and there's a lot of stuff that has to be done. Okay. So we're going to add an electrophile to the benzene ring. And when we add that electrophile, it is going to add to the double bond, a double bond, so that we form the carbocation. And then we can draw the resonance structures for that, which would be the intermediate that's on this slide. So if this was not a benzene ring, we would have to think about, do we get a 1, 2, 1, 4, or 1, 6 product? And we get none of those. Because in order to reform the superstable benzene ring, we're just simply going to lose this hydrogen and then reform the conjugated benzene ring system. So that in the end, we're going to end up substituting the electrophile for the hydrogen that was on the benzene ring. Okay. So that's electrophilic aromatic substitution versus electrophilic aromatic addition, where we would add a nucleophile then to the carbocation. So at the benzene ring, we're going to do substitution. And so the only question is then, how do we make all of our different electrophiles, which is what we're going to talk about today. And then we'll just get to a point where what happens if it's not benzene? Because if it's not benzene and it already has a group on the ring, how does that group that's on the ring affect how the benzene will react? So this is where we were at on Monday. All right. So we form the substitution product because it's more stable than doing addition. So here were some of the reactions we started with. So I need to form an E+. So what can I add to the ring? Well, if I take nitric acid and protonate it with sulfuric acid, and then that nitric acid protonates, loses water, we end up with NO2+. So I can make nitrobenzene. If I take sulfuric acid and SO3, that's called fuming sulfuric acid, because when you take the cap off of it, there's a big puff of white smoke that comes out. That's the SO3. You just simply protonate the SO3 to form SO3H+, and that is what we call sulphonic acid. Why is that sulphonic acid important? Because I can change that sulphonic acid into a sulfonyl chloride. And that sulfonyl chloride then, if there was a methyl group on the end, that would be our tosyl chloride that we use to make tosyl esters. So that's where they come from. What reagent do I add to convert an OH to a Cl? SOCl2 or PCl3, any of those reagents we learned in the past. So we can convert the sulphonic acid to the sulfonyl chloride. You can go ahead and add either Br or a Cl. All you need to do is to take the Br2 and the Cl2, but you need a catalyst. The catalyst is either FeCl3, FeBr2, or AlCl3, AlBr2. And what happens in this case is that if I have my bromine and I add to it AlBr3, what happens is that the bromine-bromine bond breaks, and basically that bromine goes over and adds to the aluminum. That leaves you with a isolated Br plus and an AlBr4. Altogether, that has a negative charge. And you could do the same thing with iron. So Br2 and benzene will not react. Br2 with FeBr3 or AlBr3, it will react. So we need that catalyst. But again, for these reactions, there's nothing really spectacular here. Each and every time, all I'm doing is forming an E+. And that E+ is adding to the benzene ring in the mechanism that we talked about last time. Okay, so here's 3 E+ that I can make. And these are good. But what I'd really like to do is to add a carbon group. So what I'm going to do there is I'm going to skip ahead and not be able to erase what was there. Well, let's see if I have an empty slide before I get to the end. Yes. Because, okay, so I can, before I go all the way back, your next slide had James Kraft or Friedel and Crafts. I forget what their first names are. Yes. So Charles Friedel he's known for other things, actually. He developed a method to determine the absolute R and S configurations from X-ray crystallography. They're called Friedel pairs. I think it's the same Friedel. But Crafts not spelled like the cheese. So a Friedel-Crafts reaction, the Crafts with a K is as annoying as a ketone with a Y. It's just like fingernails on a blackboard for me when you spell ketone with a Y. No, it doesn't have a Y. It's Ketone. So they won Nobel Prize. They're known by all organic students, including you, because they found a way to add a carbon to a benzene ring. Now, given the fact that we're how many years in the future, we should be able to do that with what we know at this level. So here's my question. All I need to do is form a C+. If I form a carbocation, it will add to the benzene ring. That's all Friedel and Crafts did. So what if I take my tertiary butyl alcohol? Can we make a carbocation out of that? Add what? Add an acid to it. And it would be better if that acid wasn't HCl or HBr. That acid should probably be something like H2SO4 so that its conjugate base isn't nucleophilic. So if we do that, what are we going to do? We're going to end up protonating the oxygen, I mean, how many thousands of times, well, thousands is me. How many tens to hundreds of times have you done that? A lot. So then we're going to break the bond, and I'm going to form my tertiary butyl carbocation. So before I get to the Friedel-Crafts alkylation reactions, I'm going to point out here that we already know how to make a carbocation. And if we can make that carbocation, it's now E+, and it's going to add to the benzene ring. So you want to add a tertiary-butyl group? Just use tertiary-butyl alcohol and add sulfuric acid to it. What's another way that we know how to make a carbocation? How about the double bond? What could I add to this double bond to make a carbocation? Anybody? What? Yeah, the water will probably have to go with it, but H+. What kind of H+? If it's me, I'm using something that, again, doesn't have a nucleophilic conjugate base. So what am I doing? I'm going to add the H+ by Markovnikov addition, and I'm going to then get a tertiary carbocation. That tertiary carbocation now becomes my E+, and it adds to the ring. So if you go back and you look at some of the older exams for third exams or second exams, what you're going to find is I sometimes ask a question about, usually it's either Pat, which is a good gender neutral name, or Dr. Organovich, which is a takeoff on the Dr. Marinovich, which was Dr. Setter's high school chemistry teacher, and that's what's in analytical. He makes all of his problems about him. There's a Perfumovich for instrumental, but I digress. If you go and look at that, one of the questions I'll ask is that somebody tried to do, like, add HCl to an alkene in toluene or in benzene as a solvent. Why didn't they get the product that they anticipated? Well, it goes to the point that if I'm going to add HCl, if I'm going to make a carbocation, the one solvent you do not want to make it in is an aromatic solvent, because that electrophile, that carbocation, will add to the solvent and not add to whatever you're trying to do. So we don't use aromatic solvents to do like SN1 reactions, or even E1 for that matter. Okay. Not unless I want to add the carbon group to the ring. Okay. And that's what Friedel and Crafts won the Nobel Prize for, was their ability to do this. But now we know tons of methods. Well, 2. But that's pretty good. Okay. So now I have to go all the way back. How did Friedel and Crafts do it? Well, what they decided to do was to use the iron or they decided to use iron or aluminum trichloride. Since I can't erase that, I'll just draw over it. So what they did was they decided, I'm not going to wait for tertiary butyl chloride to just lose a chloride. I'm going to make that happen immediately. And one of the ways to do that is to add aluminum trichloride, so that you basically break the bond, the chloride goes over, and you form your tertiary butyl carbocation plus then the AlCl4 minus. So by adding aluminum or iron trichloride to an alkyl halide, you will make you'll make the carbocation. So this is typically called Friedel-Crafts Isolation, is when you use an alkyl halide plus aluminum trichloride. And the modification on that is to use iron trichloride. It has one small problem, and that is that the reaction is subject to carbocation rearrangements. I'll give some examples of that. But that's how we can do alkylation. They also then applied that same method to a carboxylic acid chloride. And the carboxylic acid chloride, then that chloride is then removed and Cl minus goes to the aluminum, and you end up forming what's called an acyl carbocation. Right? In my lab class, we talked about this acyl carbocation when we talked about alpha cleavage. This is a very stable carbocation because I can take this lone pair, move it down, and then form the triple bond with the oxygen having a positive charge. So acyl carbocations are stable because there's more than one resonance structure. But this is the form that's going to add to the benzene ring. So what that's going to let me do is that's going to let me add any what was an acid chloride. That's going to let me add any length or any type of R group here and make what's called a phenyl ketone. It's a phenyl ketone because it's got a phenyl group that's attached to the ketone. There's not a whole lot of creativity in any of these names. Okay. So we can make phenyl ketones by reacting acid chlorides with aluminum trichloride, and this is called Friedel-Crafts Isolation. I'm adding this acyl group to the benzene ring. Okay. Same methodology. Now you may say, where does the carboxylic acid chloride come from? The carboxylic acid chloride comes from taking a carboxylic acid and reacting with SOCl2 so that you replace the OH with the Cl. It's the same thing that we just did with the sulphonic acid. We replaced the OH with the Cl by using SOCl2.
So it's called the phenol ketone. So
the phenyl. So okay, what does phenyl mean?
that's where the oxygen, the OH group was attached to.
Right, that's phenol. That's phenol. Phenol is a phenol group is when you have a OH attached to the benzene ring. A phenyl group is when the benzene ring is the substituent. And you might say, why don't you call it a benzyl group? Well, because a benzyl group is very specifically that with the CH2 on the end. So this is benzyl, this is phenol, and then this group right here is the phenyl group. So that's the terminology that we use. So when you call this a phenyl ketone, it's because whenever benzene is used as a substituent, it's called a phenyl group. Because benzyl means something completely different. Okay, so Friedel and Crafts, all you got to do is take an alkyl halide, react it with aluminum trichloride, make a carbocation, it'll add to the ring. You want to add a carbonyl group? Great. Any carboxylic acid you want, react it with SOCl2, make the acid chloride, same thing, iron trichloride or aluminum trichloride, and you go ahead and you add it. Now, you might say something like this. So how does it work with ethyls and methyls? Because it will work with ethyl and methyl. So if you take this benzene ring and you add to it ethyl chloride along with aluminum trichloride, how does the aluminum completely pull the chlorine off? Because in this case, what we would expect is we would expect that this aluminum to completely pull the chlorine off. Well, that gives me a CH2 plus, which is a primary carbocation, which many of you know we're still not allowed to draw in this lecture class. So how does that work? Because it does work. So what happens is over here, the aluminum, it's sort of a transition state where the aluminum is pulling the chlorine away. It can't pull it completely off. But once it gets to a certain point, this carbon becomes delta positive enough that it then adds to the benzene ring. So it doesn't have to necessarily be a full positive charge. It just has to be delta positive enough here so that then it can go ahead and add to the benzene ring, and then the chlorine goes to the aluminum. So it's not a carbocation mechanism. It's just forming enough delta positive to get it to work. So that's how methyl and ethyl work. They'll still work, it's just they will never form a true carbocation. And so then we can add those two alkyl groups easily to the benzene ring. What we cannot add is we cannot add groups that will undergo rearrangement. And we'll do this from scratch. We're not going to go through all those slides today. There's some for Friday, just in case you're wondering. So when we try and take it something like a propyl or a butyl group, and we want to add AlCl3 to that, the problem is as the chloride gets taken by the aluminum, we're going to end up doing a hydride shift. You can't do a hydride shift with methyl, and you can't do a hydride shift with ethyl, but you can with propyl and everything else. So if you would like to add a straight chained alkyl group to the benzene ring, you cannot do it. Because what will happen is as the chlorine gets pulled off, the hydrogen will then shift, so that what I'll end up doing is I'll end up forming a secondary carbocation, which is perfectly stable, and then I end up adding the rearranged carbocation to the benzene ring. So I can't do that. I can't add a straight chained alkyl group to the ring. So in this case, if I tried to do this reaction with benzene, what I would end up forming is I would end up forming over here the secondary butyl secondary butyl benzene, not N-butyl benzene, which is what I wanted. So anything that can undergo rearrangement, there's an issue with Friedel-Crafts. When I've talked about rearrangements the first time, which would have been like first semester, the example I like to use is this one. So back a long time ago, when I taught lab at The Ohio University, we were going to add a T-butyl group to a benzene ring in lab. And so the compound we should have used was tertiary butyl chloride. That was my intent, was to use tertiary butyl chloride and react that with FeCl3, make the tertiary butyl carbocation, and add it to the benzene ring. But instead, I grabbed isobutyl chloride and put that out. And about halfway through the lab, some young scholar said, "Hey, we're using sec-butyl chloride, or not sec-butyl chloride, isobutyl chloride, and not tertiary butyl chloride." And I said, "Okay, well, you're going to get the same product anyway." And they didn't believe me. So they questioned me thoroughly. And I said, "Well, okay, we'll make this a post-lab question then, and you can prove it to yourself that you're going to get the same product." And that pretty much ended that discussion. Then I had to make sure I was right, which I was. Not always, but most of the time. So what's happening here? The aluminum is going to grab the chloride away, and this hydrogen is going to shift over so that you would make then the tertiary butyl carbocation. And this is the first time, honestly, that I saw that carbocations were real. This is the first real example I saw that this stuff happens that's in the book. Because if you do this, you'll end up with tertiary butyl benzene. And we GC'd the product, and sure enough, that's what we got. So that is kind of an extreme example, but that's what happens. So the problem with Friedel-Crafts is you can have rearrangements occur. And they're the same kind of carbocation rearrangements that we had, last semester and earlier this semester. So we have to be careful. Now, one of the ways to get around this, and there's really kind of no way to get around this one per se, but the way to get around adding a straight chained alkyl group to the benzene ring is to change the mechanism a little bit. By mechanism, I mean approach. So here's what we do. Okay. If I want to add a straight chained alkyl group to the ring greater than 3 or greater, what I need to do is I need to first of all do a Friedel-Crafts isolation. Take the acid chloride, the aluminum trichloride, and add the acyl group and make the phenyl ketone. Once I make the phenyl ketone, I now need a reducing reagent that, when we think typical reducing reagents like lithium aluminum hydride or hydrogen gas, maybe with Raney nickel, I'm going to end up over here with an OH group. I don't want that. I actually want to get rid of the entire carbonyl group. So in order to do that reduction, there's 2 reagents that'll do a very good job. One of them is called Clemmensen Reduction. So in Clemmensen reduction, what you do is you take zinc and mix it with mercury to make an amalgam. The zinc mercury amalgam isn't really toxic anymore. This is what they used to make mercury fillings out of for teeth, was to take a metal and react it with mercury. They didn't put pure mercury in your teeth, because then you'd end up with neurological disease, and like the Mad Hatter, you'd be neurologically insane. So they use this. They don't use those anymore. Now they use glass ceramic materials. But we use a zinc mercury amalgam along with HCl and heat. And this reduces the ketone down to a CH2. Not a mechanism we need to worry ourselves with. A reagent we need to worry ourselves with, because that's one of the two reagents we can use. And so once I make my phenyl ketone, just reduce it down to the alkyl benzene. So this is a way of getting around that rearrangement. This is probably the only really good use of the Clemmensen or the next one, the Wolff-Kishner reagents, because they always go together with electrophilic aromatic substitution. So the Wolff-Kishner reduction then is, and we'll talk about this mechanism a little bit in the future, but the first thing you do is you react the phenyl ketone with N2H4, which is called hydrazine, and that makes a hydrazone, and then you react that with KOH and heat, and that will then reduce the carbonyl all the way down to the alkyl group. So if you want to make a straight chained alkyl benzene, you start with benzene and whatever straight chained carboxylic acid chloride you'd like. React that with aluminum trichloride to make the phenyl ketone, and then use either Wolff-Kishner, this is a W-K, or Clemmensen in order to do that reduction. Now, do you have the option of writing W-K and Clemmensen? Not for full points. So you need to remember one of those two sets of reagents. And one of them's better than the other, but I don't care. They both do the same thing. So there's ways to work around some of these reactions and some of the limitations.
For the Wolff-Kishner, we're going to have to write out the two separate steps.
No, Wolff-Kishner normally, the Wolff-Kishner reagent would have been, you would write N2H4 N2H4, and then you can write KOH and heat. Yeah, this is the combined. That's the Wolff-Kishner reagent. We'll talk about how we form hydrazones later. I don't know that we'll talk about the reduction down to a CH2 group, but we'll talk about hydrazones in a while. So, okay. So at this point, these are some of the methods that we can use to form E pluses that can add to the benzene ring. And that's all we need to do. So if I want to add a group to the benzene ring, I just need to create that E plus. So that's great. Kind of easy though, because when you have a benzene ring, it doesn't matter where you add the group. Because you got 6 hydrogens, you can replace any of those 6. So let's make it a little more complicated. So now let's do reactions of substituted benzenes. So as it says here, you know, never good to read directly off the slide, but I'm going to do it anyway. When a monosubstituted benzene ring is reacted in an electrophilic aromatic substitution reaction, the substituent has 2 effects on the reaction. So now what I'm going to do is now I'm going to add a group. Okay. And I'll get to what all of this is. Number one, let's talk about it can cause the reaction to occur faster or slower than benzene. So in other words, any group I put on the ring will go either make the ring react faster or slower than just having a hydrogen there. Now, what do we call the groups that make the reaction go faster? Activating groups. What are the groups that we add that make the reaction go slower? Deactivating groups. That's great, but doesn't really tell me much. So now I have to think about, well, what are these groups doing to make this reaction go faster or slower? So then we go back and we remember, well, what am I doing? I'm adding an E plus to a benzene ring. What's the E plus? It's the, what's the E stand for? Electrophile. So it's the electrophile. What's the benzene ring? It's the nucleophile. The electrophile is electron poor, and the nucleophile is electron rich. So how do I make the benzene ring react faster? Make it more electron rich. Faster. More electron rich. Okay. So activating group. What makes an activating group? A group that's going to make the benzene ring more electron rich. So what is that group going to do? That group is going to donate electron density to the ring. Any group that donates electron density is going to be activating. Any group that takes away electron density, making the ring less rich, is going to be deactivating. So that's what those terms mean. And so now what we need is we need a list of groups. We need to figure out why they donate or why they withdraw electron density, how they do that by inductive or resonance effects. So that's the first thing, is does it make the reaction occur faster or slower? So we have activating and deactivating groups. Great. Now what's equally important and hopefully related is if you have a group on the ring already and you're going to add an electrophile to it. So in this case, let's say I write toluene with the CH3 and I'm going to add to that HNO3 with H2SO4. The first thing I need to know is I need to look at these reagents and figure out what the E plus is. Right? And the E plus is NO2 plus. It takes a little longer when it's not written on the board already, I found. Even though that was only 45 minutes ago. But that's the first step. The first step is look at the reagents. What's my E plus? Then that's the E plus that I'm going to substitute into the ring. But now I have a problem. Because before when it was just benzene, I could put the group anywhere I wanted. Now with another group on there, should I add that NO2 group ortho? Should I add it meta? Or should I add it para? So again, what was the point of this? When you put a group on a ring, it affects the ring in two ways. Number one, the ring reacts faster or slower. Number two, that group is now going to be the director. And that group as the director, that methyl group as the director, is going to tell that NO2 where to go. You go ortho to me, you go meta to me, or you go para to me. But that group does the direction. And hopefully these two things are related somehow. And fortunately they are. So here's some groups that when they're attached to the benzene ring, these are ordered from reacting fastest, number 1, to reacting slowest, number 10. So ideally, at some point, I'm going to make a 1 to 10 completely vertical list out of this. But what I've done is I've split it in half. Because here's benzene. So the first 4 groups cause the benzene to react faster. Those are my activating groups. Then these rest of the groups, these 5, make the benzene react slower. So those are the deactivating groups. So if you look at the activating groups, the number 1 is an N, anything with an N and a lone pair. Second is anything with an oxygen and a lone pair. Third is another benzene ring. And fourth is an alkyl group. So those 4 groups all make the benzene react faster. Remember a long, long time ago, another long, long time ago, when we had graduate students in the chemistry department, one of my graduate TAs she was adding iodine to the ring by some new fancy green method. And so she said, well, what's the most reactive benzene that I could use? And I said, one with a nitrogen attached to it. So she went to the stockroom, she found something with the nitrogen. The next time I saw her, I said, how'd that reaction go? And she goes, yeah, a little too reactive. It blew the stuff all over the hood, and it took me like 2 hours to clean it up. And I said, sorry, you asked which one was the most reactive. So a little too reactive. Or not enough ice to cool it down and control the reaction. So nitrogen and oxygen are the first 2. And we could go through literally 4 mechanisms here. Because now we got to explain, well, where does that direct? Or better yet, how are those donating? Shouldn't get too far ahead. How are those groups donating electron density? So what I'm going to do is I'm going to actually summarize these 2 guys as saying anytime you have an atom with a lone pair attached to the ring, it's going to do this. And it's going to cover both nitrogen and oxygen. That's not going to be helpful for the ring, and it's not going to be helpful for the alkyl group, but we'll figure that out on Friday. On the other side, we have halogens, carbonyls. Doesn't matter what kind of carbonyl. I'm not going to be fussy. I don't care whether it's an aldehyde, ketone, etc. I'm just going to lump them all together. Then we have C triple bond N, which is a cyano group or a nitrile group. Then we have our NO2 group. And then we have an N plus with an R3. So actually this one, sometimes people will say you don't get any reaction when you try and add an E plus to a ring that already has an N plus on it. And that's true. Because an E plus wanting to react with something that already has a plus charge on it, the pluses are going to not go together well. Okay. So what we need to do is we need to go through, which is what the rest of the slides do. So hopefully you'll be able to stay awake on Friday. But we're going to go through, okay, how does each one of these groups stabilize? Or how do group push electrons? How do they pull electrons out? And then once we do that, we'll be able to figure out, okay, how's it direct? And we're going to find that it either directs ortho and para or meta. So again, it's the yin and the yang of organic chemistry. You want orthopera, you got a way. You want meta, you got another way. So that's what we're going to talk about on Friday. So I think we'll finish up these notes and then talk about some other reactions that we could do with benzene rings. There's no homework or take-home quiz problems for Friday. I will take your take-home quiz problems from today up here. And see you on Friday.